afternoon. Welcome to this lunchtime lecture, the final in our webinar series for climate action sustainability. Thanks for you joining us for lunchtime, whether it's your first or you've been with us for more than one session. My name is John Gallagher and I've been coordinating this series. And here we are, the final in the series. We are Wednesday, the 10th of May, having come through from early February, and I hope that you have enjoyed participating and enjoying the our speakers throughout the series. As always, these are recorded and are available after, so that you can look back, you can share, and we welcome your responses as to whether you're enjoying them or finding them useful. And please, given that this is planned for the future, please do liaise with us if you would like to hear specific topics being addressed in this space. Really what we're here for is sharing knowledge and perspectives. And I suppose we contextualize it as all our speakers, and our speaker today will also contextualize it during his talk, how our work that we do in terms of research, in terms of outputs, address national and global climate action and sustainability challenges. In that context, from a national perspective, we have priorities as defined in our climate action plan, whether it's energy, travel, greening business, enterprise, land use, etc. These areas are hugely important to us achieving our targets. And then we are part of a global society. We also must consider how our local and national ambitions align with global goals, such as the SDGs. And really, it's been an insight to see how each of our speakers throughout the series has connected their work to these actions and priorities and goals. And so really today, we're going to finish out the series with the continued challenge that we face with regards to the need for energy. And I welcome our speaker, Professor Max Garcia Melchor from the School of Physics, who's going to give a talk titled Materials Discovery for Power to X Technologies. Now, I'm curious what X stands for, and I'm sure Max will give more insights during his talk. But as energy is still going to be a big part of our needs for the future, where do we source it? This is a great segue from our session last week that looked at decarbonizing aviation. Now we have to look at our energy needs and what types and what are the challenges that we face with regards to resourcing that. So Max, I might stop sharing my screen and hand over the reins to you. I'm going to stop sharing. For everyone, as Max prepares the slides, please do add your questions to the chat. Please don't be shy. Raise your hands later on. Max will be happy to take your questions. And so after the next half hour or so, we'll come to Q&A and look forward to the discussion. Max, thanks for joining and look forward to your talk.
Thanks very much, John. First of all, thanks for the introduction and thanks for organizing these lunch webinars. They're really good. So I'm delighted to be here today. And I'm hoping today with my presentation, to give you an overview of what Power to X technologies are, why I believe they will be so important in the coming years and in the future, and how we can use essentially computers to accelerate the materials discovery in order to enable this transition. So let me just start with this slide because I want to set the context and the big picture. So this is an illustration of the energy consumption data taken from the International Energy Agency. This is from 2010. I'll show you in a minute more recent data, but you can see how essentially our society relies heavily on fossil fuels, right? So 32% of our energy comes from oil, 21% comes from natural gas, and 28% comes from coal. And when we look at the stake of renewables and other energy sources, you can see that it's fairly small, right? This is from 2010. So if you wonder how much has the picture changed in the last, in 9 years, here you have the numbers, and you'll see that, essentially the percentages have gone up or down by 1-2% maximum, right? So we still rely heavily on fossil fuels, and we know that has a huge impact in climate and the emission of greenhouse gases. So we urgently need to stop relying on fossil fuels, and ideally we would like to switch entirely to renewable energies, right? And there are many options here. So we can rely on hydropower, wind power, solar energy, geothermal energy as well. And they're all great, right? And in the case of Ireland, I'm going to show you now that the situation is not much different. So Ireland also relies on fossil fuels, especially oil and gas. And we have a little bit of renewable, especially wind, and I'll come to this in a second. But most of this energy goes into transportation, residential, powering homes essentially, and industry, right? And so if we look at renewables, we're lucky, we're not in a bad position because we're very fortunate to have a lot of wind, right? For good and for bad. And so if we look at this picture here, we are quite strong in terms of wind energy. And actually, when you look at the map of the entire Ireland, you'll see that there are loads of wind farms that have been developed across the island. And in fact, wind energy is the largest and the cheapest renewable energy source that we have nationwide. In fact, in 2020, about 86% of the wind energy that we produced came from wind energy, right? And this amounts 36% of the total electricity demand. So we're quite strong. And in fact, we're the second world leader in terms of wind energy production behind Denmark, which is great. Now, I'll show you in a minute, other metrics. These are more recent. This is data from 2022 from the wind energy report, from Wind Energy Ireland. About 34% of Ireland's electricity came from wind in 2022, just 2% short compared to 2020. We're still the second best country in wind energy production, and there is a lot of investment going into developing new wind energy farms, which is always welcome. We are very ambitious, and we have set really challenging targets by 2030. So the National Climate Action Plan has set this goal of having 80% of all our electricity coming from renewables, in particular from wind energy. And that means that by 2030, we'll have to build about wind farms that can provide 8 gigawatts of inland wind energy and about 5 gigawatts of offshore wind farms. That's quite substantial, considering that currently the capacity that we have, it's 5,500 roughly, and the energy consumption from 2021 is about 28,500 gigawatts per hour, right? So here I'll leave this as an open question based on how far we need to go, the energy consumption. I'll leave here the question of, will this be enough in order to transition and decarbonize our society? And I'm going to show you also some additional data, and then you'll be able to probably analyze yourself the data and come to a conclusion. So this is also interesting data from the census from 2022, so from last year from the Central Statistics Office. And here you will realize that last year we reached a record. So for the first time, the population in Ireland exceeded 5 million, right? And that was because there was the natural increase in population, which is always welcome, and also the net migration of people coming to Ireland, right? So you can see that in the coming years, so in the next years by 2030, which is when we'll need to meet the that 80% target, the population will continue increasing, right? So that means more energy will be required. Also, something to bear in mind is what we call the dispatch down. So the dispatch down is essentially the wind energy that is wasted or not utilized. And that could be for a number of reasons, could be for due to technical issues, so it could be because there's an excess of energy compared to the demand, and that energy is essentially wasted, right? So if you look at the numbers of how much energy was wasted, that was 12.1 of the entire electricity produced from wind energy was wasted in 2020, and that went down to 7.4% in 2021. Still, it's a massive amount of energy that we're just letting go away. Another issue with wind energy, and in general, most of the renewable energy sources, is that they are intermittent, right? So we know that we don't have wind every day or at all times, and this is a plot actually illustrating this. So this is the wind generation in gigawatts here in dark green, and in white you see the demand. You see that in most cases the generation exceeds the demand, which is great, but then you can see how the generation and the demand oscillates throughout the year. And these oscillations in wind energy production and demand is what makes the prices to go up and down. So that it's obviously not ideal. We would like to have, you know, a constant price and get always the same bills throughout the year. And most importantly, we want a source of energy that it's clean and renewable and that can be accessed at any time, right, throughout the year. So one option is to store electricity, this excessive renewable electricity, rather than just letting it get wasted. What we can do is to store it. And one can think of, for instance, lithium-ion batteries, because they are very popular, and we have them nowadays in almost any electronic device. So in our phones, even in our cars. Now, the issue of lithium-ion batteries and batteries in general is that nowadays they are quite heavy and they take a lot of space. Most modern batteries, they rely on lithium. Lithium is a quite abundant element, but it's also mined in very specific areas in the world. So there might be some geopolitical issues. And if one thinks that the number of electric vehicles is increasing and they all use lithium, as well as all the electronic devices, then we might run eventually into issues with the sourcing of lithium, right? And that might increase the price, and that will reflect into, you know, cars and other electronic devices being more expensive. Now, having said this, there are a number of non-lithium ion batteries that have been or are currently being developed. The issue is that at the moment, as far as we know, they're not commercially ready, you know, to reach all the population, right? Another option is to store this excessive renewable electricity into chemical bonds, right? So what you do is you use this renewable electricity, you run a chemical reaction that requires some energy input, and then you create new bonds, and this energy is stored in the form of chemical bonds. And this is what we call the power to X concept. So you use renewable electricity to form X, and this X could be chemical fuels, which you can directly utilize, or they could be chemical feedstocks, so chemicals that you will then use to produce other goods. So if we look at these power to X, and that would be the focus of my talk, there are many things you can do. And here is a summary of, if you wish, the ideal world that we expect to see in the coming years. So you take renewable electricity and you run, for instance, chemical reactions using abundant molecules like nitrogen, which is present in the air, or CO2. So you could reduce CO2 from the atmosphere, which is one of the main greenhouse gases, or convert water, which is very abundant as well, into chemical fuels or feedstocks. So for instance, nitrogen, you could reduce it and produce ammonia. And ammonia is very important because it's used in the production of fertilizers, which is what allows us to harvest food and produce all our food. But it's also very important in the production of all the nitrogenated compounds. CO2, it's a very abundant greenhouse gas, and it's something that we could use to generate carbon-based compounds that could be either utilized directly as a fuel to power transportation, or again, they could go back to the chemical industry and used to, for example, to produce polymers. The reaction going from water to hydrogen, that's known as the water splitting or water oxidation. This is also very attractive from, again, a chemical perspective, because hydrogen is a molecule that is widely used in chemical industry, but also as a fuel, because if we could store this hydrogen, and this is what we would call green hydrogen because it comes from water and it doesn't have a carbon footprint, then this hydrogen could be used in a fuel cell along with oxygen present in the air. And then we generate electricity. And at the same time, we're only releasing water, so no carbon footprint with this energy vector. So that's very interesting. But for all these applications, which some of them are listed here, we need materials because all these are reactions that are very difficult to carry out, and they need some energy input, and they need some promotion, some catalysts, right? So this is what I'll be mainly talking about today. So because of the breadth of all these reactions, one can think of materials discovery essentially contributing to address most of the priority areas in the climate action plan, because we'll need materials for, develop renewable energy technologies. To build better, we'll need more sustainable materials. The way we travel, as I said, we could use these chemical fuels that we can produce from Power-to-X technologies, which have a lower or no carbon footprint. The way we consider farms, we can make them more sustainable if we can make ammonia, for instance, and fertilizers more sustainably. The way we run our enterprise, so how we use the land to store, for instance, carbon dioxide, it's very important. And materials research can help us addressing all these areas. Now, in my case, my particular research expertise is in developing materials for these applications for powering renewables. So we try to accelerate the discovery of materials to enable this transition and produce chemical fuels which are more sustainable, and also finding ways of electrifying chemical reactions. We are also doing substantial work in the sustainable production of ammonia and other nitrogenated compounds, as I'll show you in a minute. And also in, one can think that our research might in the future help decarbonizing the industry, because the way chemical reactions we hope to run in the future will be more sustainable, so release less greenhouse gases to the atmosphere. Okay, and these main areas are mapped into these development goals, these SDGs, in the ones that I'm listing here. So affordable energy, zero hunger. If we consider that we hopefully will be able to produce more sustainable fertilizers, climate action plans, sustainable cities and communities. And we're also obviously trying to nurture and attract talent and educate the future leaders in this field. Okay, so this is my research group at Trinity. So the name of the group is Computational Catalysis and Energy Materials Group. We work on these 4 different areas. As I said earlier, there is this common goal of trying to develop processes by developing materials that can promote chemical reactions that utilize earth-abundant reagents that we have in our planet, renewable energy sources, in order to produce chemical fuels or chemical feedstocks or added value products. Right? That would be the common theme of our research group in Trinity. Okay, so the question, I suppose, is how do you develop a catalyst? how you come up with a material which works well for a given application. And this is essentially the toolbox that any chemist works with, right? So this is the periodic table, and one can think, well, with some chemical intuition, I know that iron might be a good material for applications A and B. But then if we want to improve the activity or the performance of this catalyst, one can think of maybe nickel might be also a very good candidate. Now, the question then arises when we think that why not combining two elements of this periodic table? Maybe nickel and iron have some synergy, and they can offer you a better activity or selectivity towards certain products, right? But then if you say two elements, why not adding a third one, right? And when you start adding new elements, then this is just an exponential problem. And this leads to, if you do the math, this will lead you to this number of combinations of different elements. And that's obviously something that is intractable, right? This number is actually higher than the number of atoms that exist in the known universe, right? So it's something that it's intractable. So we need to find alternative ways to choose these elements and know how to combine them. Now, if you want to do this in the lab, and there are lots of high throughput experiments that are currently being developed, this is something that can take between months and years, right? Because when you think that you need to buy the materials, you need the reagents, you need to make the materials, you need to characterize them, you need to test them, right? That can take a long time. In order to speed up the process, in my group, what we do is to use computational chemistry. So we use computers and quantum chemistry in order to accelerate this process. So essentially, we can model chemical reactions in our own laptops. All we need is a decent laptop and a dedicated software. Now, the trouble is that this would accelerate only a little bit the process that would be carried out in the lab, right? So how do we go from a time scale that is in the order of months, years, to ideally days or weeks? And for this, what we use is supercomputers or high-performance computing centers. And these are dedicated facilities that can contain up to millions of CPUs, right? So what we do is we prepare our simulations in our own computers, then we connect to these supercomputers, and this is where we run all our simulations. Okay, so how we accelerate this, what we call rational catalyst design, right? So we start with a real catalyst, something that maybe works, and we try to improve it. What we can do is, with computational chemistry, we can look at the atomic scale. So that would be a representation of the real catalyst. And with this model catalyst, we can actually look at chemical reactions on the surface. And not just the chemical reactions that we're interested in, but also how our material can react with other substances that might be in solution, right? And we can calculate this stability diagrams in different conditions and thermal conditions, or even under the application of a bias. And then with this, we can extract very valuable information, because we can not only predict the stability of a given material, but we can also know what's the state of that surface of the material under real reaction conditions, right? And this is important because once we understand how our material behaves in all-round conditions, then we can go to our experimental colleagues and suggest the optimal experimental conditions. Now, once we have this information, then we can look at how these reactions that we're interested in work at the atomic scale. And not only the reactions that we're interested in, it's also very important to understand what other reactions might also be competing at the same time, and that sometimes can lead, or are one of the main reasons for which the catalyst just stops working, right? Once we understand what happens at the microscopic level, then we can predict the activity of a given material or the selectivity. And once we understand and we're able to predict this, we can propose what we call reaction descriptors. And what are these descriptors? Well, a reaction descriptor can be anything ideally something that you can easily calculate with your computer and that it doesn't take much time. And it's a property that describes the catalytic activity or the catalytic performance, right, of your material. And this is very important because if you're able to find such a property, then you can automate the generation of different materials, calculate this property, and this is how you can really speed up the discovery of new materials for targeted properties. And one can think of, once we have lots of data, then we can also use artificial intelligence or machine learning. And now we'll be talking about not just a time scale of days or weeks, but actually we would avoid using all this quantum chemistry and be able to make predictions within seconds. So that's obviously the dream, but I'm going to say a few words of caution about this, right? So let's say that we are this guy here and we want to discover a catalyst, which, if we wanted them to last and be really, to fulfill the purpose, we need something that is cheap because we don't want to replace it every now and then. It needs to be active, selective, and easy. So this is what we call the case principle, right? Now, the issue with many high throughput and artificial intelligence studies is that when they start, they get lots of data and the machine learning models start searching, right? And sometimes, depending on the data you use, actually, rather than accelerating catalyst discovery, you might be decelerating catalyst discovery because your artificial intelligence models, what they are doing is they're walking essentially in circles, right? And that's why it's important to avoid this and go straight from the simulations to the target material. We need to use data, which is not only chemically plausible, and that means things that can be made in the lab, right? Because otherwise it's completely pointless to predict something that cannot be made in the lab, but also data that we use in our models that it's representative. So materials that we know will resist and will be preserved under reaction conditions. Okay, so with this in mind, let me just tell you what we have been doing in these three main different areas. So we're a group that has been doing a lot of work on developing materials for green hydrogen production. In particular, in the past, we have used these reaction descriptors that I'm plotting here on the y-axis. It's one example, in order to rationalize the activity and the performance of materials for green hydrogen production, right? So all you need to know is that this blue region here is the optimal value of this descriptor. And with this descriptor, you can, for instance, see why or how doping a material, in this case, it was a nickel oxide supported on gold, how doping it with cerium gives you a value of this descriptor that is closer to the optimal value. We can also understand with this descriptor what happens when you introduce the support, so when you introduce gold. And it allowed us to explain why only when you have this gold support and when you dope it, and on top of this, you have this very special coordination environment, you actually get to find a material for which we predicted the optimal descriptor value, right? And that was something that was made in the laboratory, the experimental laboratory of Professor Thomas Jaramillo at Stanford University. But there is more that you can do with these descriptors, right? And this is something that we did. In this case, we took this descriptor, so how strongly no-wage moiety binds to the surface of the catalyst. And at that time, we knew that these three different materials have different binding of this intermediate. And then we started mixing these different materials. So we generated binary oxides, and we found that when we mix them, we always get something in between, a predicted descriptor value that was in between the original two values. And as you can imagine, this is the optimal value. So the next calculation we did was to combine this binary materials in order to generate a ternary oxide. And indeed, we predicted an optimal descriptor value. So this is something that luckily our experimental collaborators in the group of Professor Edward Sargent, now at Northwestern University, they were able to make this material using this salt gel synthesis. And you can see here the characterization, how all the different elements are homogeneously distributed. And that's what makes this catalyst so well-performing. So here you can see on this secondary y-axis, this is the Faraday efficiency. It's essentially a measure of how efficient the material is in channeling the electrons, right, towards the desired product. So you can see that the efficiency was almost 100%. And here on the other y-axis, I'm showing the potential. I said that most of these reactions require an energy input. So in this case, we apply a voltage, and you can see here that the voltage doesn't oscillate. That's an indication that the material is quite robust. And you can hold this current density, and you can see that the potential doesn't change. And you can do that for about 500 hours, which is, give it or take, a month, right? So that was fantastic. That was really good news. The only issue is that these reactions were carried out in base, right? And for commercial applications, this has some limitations. So ideally, you would like to work under acidic conditions. And the reason is very simple. You have on the other side of this electrolysis cell, this is where you are producing hydrogen, right? And this process is more efficient when you have protons, and that means working under acidic conditions. So that's why we became very interested in molecular systems for green hydrogen production, because many of them are actually stable under acidic conditions. And what we did in this work was first try to understand why ruthenium complexes, they're so much better compared to any other complexes reported in the literature. And now we have reached a point where we understand what's needed and why these complexes are so stable and what's needed in order to develop an ideal catalyst, right? So we have a series of boxes that we know our materials must tick off in order to reach. This is like a peak of a volcano where we want where the ideal catalyst in principle sits, right? Now we have taken all these catalyst design principles and descriptors, and we have developed an automated approach to screen molecular complexes much faster, right? And through this work that we published a couple of years ago, we have been able to actually predict 3 new complexes, which are predicted to be comparable to ruthenium catalysts, but they're made of chromium, which is way cheaper than ruthenium. Now, where we see this field going is, obviously here we managed to model an automated generation of complexes, but we want to take this to the next level and actually build a molecular OER database. And for this, we have developed this new platform, this what we call DART, Directed Assembly of Randomized Transition Metal Complexes. This is a modular approach that what it allows you is to extract data from the Cambridge crystallographic database. This is the major database of crystal structures, so actual compounds that have been made in the lab. And then we take these complexes, we disassemble them, we generate unique library of ligands, and then we choose which are the boxes that we want to tick off. So which composition we want our catalyst to have, which coordination with type of ligands, and then we can assemble brand new complexes and calculate these new descriptors and hopefully find and predict novel materials which are much more active. Okay, so this is for the molecular side. On the heterogeneous or material side, we are still working on hydrogen. Now we have this project that was last year funded by SFI through this Frontier for the Future Partnerships Award. This is a project in collaboration with Professor Suresh Pillai from ATU Sligo, and my colleague in the School of Chemistry, Professor Paula Clavita. And the project essentially aims to use bio-derived products in order to produce hydrogen, green hydrogen again. But now this type of reaction, which we call hybrid electrolysis, have some advantages compared to the standard HER-OER. This is hydrogen evolution reaction and oxygen evolution reaction. So rather than oxidizing water on the anode and produce oxygen and protons, which travel to the other side to produce hydrogen, what we do is we keep the cathode, so the same reaction on this side, but now we change the oxidation of water by an organic substrate. And what are the advantages? Well, hopefully, there are many organic substrates which are easier to oxidize than water, right? So that reduces the energy input that you need to supply, first of all. You can also choose organic substrates that can be oxidized and form a different product, which has a higher value, right? So you can produce value-added chemicals out of bio-derived feedstocks. And finally, you can use maybe not a bio-derived or something abundant, but you can use something that it's not used, right? It has no essentially value, and just, or something that has some value and sacrifice it, right, to produce hydrogen and some other chemicals which might have the same value. And it's also a much safer process because we are for certain applications we don't have the issue of cross-contamination and some safety issues that you might have under this scheme. Okay, so this is in a nutshell what we have been doing on green hydrogen production. Let me tell you a few words about what our current efforts on the production of fertilizers and nitrogenated compounds. And I have to say that the group is also very concerned about waste and circular economy. So this is one of the biggest issues that our society will need to face as well in the coming years. So that's why in the group we became interested in a reaction where we could take cyanide, and cyanide, it's a compound that it might sound very scary, but it's actually more abundant than what we think. So it's present or produced by microorganisms. All the fruit seeds, they actually contain, believe it or not, some cyanide, and it's also present in roots, right? So we wondered, could we take all this food waste, right, extract the cyanide, and then from the cyanide, can we produce ammonia by reducing it? And then once we have ammonia, ammonia is used for the production of fertilizers. You can harvest food, and then again, you close the cycle, so you have a process which satisfies the circular economy principle. So surprisingly, the only report we could find in the literature was this very inspiring work by Federico and co-workers early in the 2000s. And they ran this reaction, this cyanide reduction, using different metal cathodes. And this is one of the few reactions, this is one of the few reactions that you will find where actually the cheapest, or one of the cheapest metals actually outperforms the precious metals like palladium, right? So this is like a dream come true. This is the overall production from cyanide, but as you can see here, you have two different colors. The gray color, that's the amount that you produce of this other chemical. This is methylamine. And the blue color denotes the concentration of ammonia that you get. Now, obviously, this is not ideal because I said that we were interested in producing ammonia. So you would like all this to be blue, right? But one of the advantages is that this reaction, if you are able to produce ammonia, you're also producing for the same price methane. And methane is essentially the main component of natural gas. So you get two chemical feedstocks for the price of one. All we need to do is try to understand and try to address why or how we can actually flip this and produce more ammonia compared to methylamine. Right? So that was the main challenge we tried to address a couple of years ago. And now we're at a point, and I won't be discussing all the details, but this is showing you how we can map out the reaction mechanism. So how we can understand what happens at the atomic scale. And we have now understood what are the reasons for the observation of methylamine as the major product. And it's very simple. This chemical, when it's formed, it desorbs the surface. And when it desorbs, then it can escape, right? And it's very difficult to retain it. And then to hydrogenate or reduce further to methane and ammonia. Now we understand better what's the role of the electrolyte, so the solvent. So there are alternatives and things that we're exploring at the moment to try to retain this species and try to promote other mechanisms that would retain the ammonia on the surface or the nitrogen on the surface to be able to produce or reduce it all the way to the end. Okay, another very interesting project that we are currently working on is this project funded by the European Commission. This is a Pathfinder project, the former FED Open projects. This is a project with several partners from Spain, from Netherlands and Germany. And this project essentially aims to take the CO2, which is dissolved in seawater in the ocean, and that leads to the acidification of the oceans. For those who didn't know, CO2 is dissolved in water and form these carbonates or bicarbonates. And so what we're proposing is, could we use this activated form of CO2 and combine it with nitrate waste? So these are fixed forms of nitrogen in order to recycle it. And then can we produce CN chemicals like urea, which is a very important chemical in industry and also very important for the production of fertilizers. So with this project, we hope to address the following challenges. We hope to reduce and recycle nitrogen from agriculture, so balance the nitrogen and carbon cycles, address the acidification of the oceans, also address the utilization of the conversion of CO2 into chemicals, and also produce CN chemicals sustainably and more selectively. And the specific role of Trinity and my group in particular will be to come up with materials that model the different reaction pathways, not only the formation of urea, but other CN products, as well as deactivation pathways, and then suggest our experimental colleagues in the other institutions to make these materials, to suggest the best candidates so that they can be made and tested in the experimental lab. Okay, and finally, we're also doing a lot of work on CO2 reduction. We have been doing for the past 2-3 years, a lot of work on light-driven CO2 reduction. So reducing CO2 using sunlight to produce chemicals. Today, I'm going to show you, or I wanted to highlight one project that was recently funded. This is a Marie Curie doctoral network, which aims to address the CO2 conversion by developing bimetallic materials and reduce CO2 electrochemically to produce chemical fuels and chemical feedstocks. This is a large project in collaboration with these 10 partners, of which they're leading institutions in advanced characterization and modeling, as well as some top companies in the field like Toyota, Apria, or Advent. Here, the role of Trinity is going to be not modeling the reaction mechanisms, but focusing more on getting the data from other groups in Italy, which will compute the reaction mechanisms. And with all this data, we hope to develop machine learning models in order to speed up even more the predictions of these bimetallic materials. Okay, so I come to the summary of my talk. This essentially was the summary of Power-to-X technologies. I hope I've convinced you of the promising feature of these technologies. Remember, X can be anything. It can be chemical fuel, it can be chemical feedstock. There's a need to develop these technologies, and if we want to meet the very ambitious targets I believe a combination of computational chemistry together with experimental studies are essential. I showed you essentially things that we can do, so how we can map out the reaction mechanisms, combine different materials. I briefly mentioned about machine learning and artificial intelligence. One needs to be careful because in order to enable this, we need databases, and we need these databases to fulfill these FAIR principles. So they need to be findable, accessible, interpretable, and reusable. But most importantly, we need databases which contain graded data and meaningful data. Otherwise, we might be decelerating catalyst design rather than accelerating. So with all this, I would like to acknowledge this is the team. This is my team in Trinity, and this is the group of really talented people and who actually do all the work and the work behind the scenes. So I'm very grateful and very lucky to have a brilliant group of students. I also have a lot of luck to collaborate. Most of the work that we do in the group is in collaboration with experimental groups, not only from Trinity, but all across the world. And we're also very fortunate to be well-funded from different funding agencies and well-resourced in terms of computational resources, because that's what we need at the end of the day to run our research. So thanks very much, everyone, for listening, and I'll be happy to take any questions.
Thank you very much, Max. So as always, you're welcome to raise your hand if you want to ask a question directly. I can invite you, or to add Q&A. We've been quite a shy audience, Max, so far. I suppose one thing I'm kind of curious about in terms of all of the different pathways that you're exploring, in terms of technology readiness levels, what sort of ranges of TRLs are some of the work you're doing? Because clearly some of it's early stage, but some of it must have been quite advanced or has advanced at this stage. So maybe just a little overview of where are all of these technologies, or in the work you're doing in terms of TRL, out of curiosity.
Yeah, that's a very good question, John. So most of the work we're doing, I would say, it's within, we have the more challenging and blue sky research going on in the group, right? Yeah. But we also have things that are more applied, and all these European projects are actually in collaboration with experimental groups. And there is a work package where we aim to actually develop a prototype in some of them. So I would say we are in TRL 3 to 4 in some projects. That doesn't mean that materials discovery can contribute to higher TRL, right? Because you can always take something that works perfectly and it's high TRL and then just try to improve it.
Yes, of course. It's not always a linear 1, 2, 3, 4, 5, 6, 7, 8, 9, so to speak. Exactly. And I think that's kind of the key thing as well, is a lot of the work that you're doing is going to take steps to as you say, replace alternatives. But one of the things that has been a common theme around materials and energy is making informed decisions. So you mentioned sustainability several times. What has driven your team's awareness of sustainability, circular economy? Is it a driving force, or is it something that your work was continuing and these kind of concepts are now aligning very well with have you changed your kind of your processes, and so to speak, in terms of your research?
I think we are continuously changing focus. And I think it's for good, right? So you start with an idea, obviously you have a research direction, right? You know where you want to go and which challenges you want to address. But the more we dig into a chemical process, we've also seen the opportunity of contributing to other chemical reactions, which we find are interesting and perhaps even more attractive from the sustainability point of view, like the cyanide reduction for a number of years, and many groups are working on reducing nitrogen to ammonia. And that's an extremely challenging reaction. So that made us think that maybe, because nitrogen is so inert, right, it's very difficult to break that bond between the nitrogen atoms. So we thought, well, why not taking something that it's already more activated or easier to break? And then we tied this with the concept of circular economy. So we take food waste. We're not aiming to replace ammonia production, right, which works perfectly fine, although it's not very sustainable. But we're trying to contribute in any way we can to make processes more sustainable.
Max, thank you very much for joining us this lunchtime and for your talk. It's made me, well, it's brought a lot of new language into my own realm of thought, and I'm sure we'll cross paths in due course in Trinity, because we don't actively cross paths. But
yeah, no, it would be
very
great.
interesting.
Yeah, it would be great. Thanks so much, John.
Thank you very much
for the invitation again.
No problem, and a great way to close, to look towards the future with PowerTex technologies, from Max. So everyone, thank you very much for joining us today. Of course, Max's work and indeed all of our speakers can be accessed through tcd.ie/research, or the individual schools in which they sit. And also Max contributes to an excellent master's in energy science program, and contributes to different undergrads and postgrad programs, and teaches this work as part of programs he's involved in. So to close, where are we in terms of our lunchtime lecture series? We've talked about many different topics. Power to X could be there now, because it addresses materials, energy systems, circular economy, technology, but biodiversity, systems thinking, mobility, other aspects of the series that I hope you've enjoyed if you've participated in multiple sessions. If not, if you're new to the series, you can get access to all of these via Trinity's YouTube channel, and as a registrant, you'll receive links to the recent talk just today by Max. So as always, we'll share the recording. Thank you for joining. Obviously, signing up to these sessions, it might be too late, but we'll be back next year for a series again on an excellent range of speakers. Who knows who they'll be at this point, but we will identify a range of speakers that provide and provoke thought and discussion with you all. Thank you very much for joining us today and through the series. Perhaps see you next time. We'll be see you next year, but have a great time. Have a great day. My contact details are there for anyone that wishes to contact me about the series. And once again, thank you very much and have a good day.